Okay, so let's go. Hello to all. So thanks for being here. Thanks, Christiane, for being here for your second distinguished lecture on oil price forecasting. So the first one was really fantastic, and I'm really looking forward to listening to the second part today. So for our members, this is recording. So this is recorded. Sorry. So you will have access online on the IIF YouTube channel. And Christiane, the floor is yours. We have about let's say 1 hour and a half. So maybe as just discussed previously, we can take questions, clarification questions during Christiane's presentation. Just raise your hand and take the floor, and maybe we can save 5 or 10 minutes at the end for let's say more philosophical questions, if any. Let's do that. Christiane, thanks a lot again for being with us at IIF, and the floor is yours.
Okay, well, thank you so much, Laurent. Let me start by sharing my screen. Also going full screen, I hope. Yes. Okay, so here we go. So welcome back, everyone. Thanks so much for joining the second lecture in this series where we're going to talk about recent advances in forecasting energy prices. So last time we focused on forecasting oil prices, which I guess these days are in everybody's minds, but actually oil prices, while still being sort of the price of the major fossil fuel, is not the only one. And in fact, there has been a lot of focus recently on natural gas as another important primary source of energy. This energy source, so natural gas, is actually very widely used across a number of sectors. So think of residential and commercial space heating and cooling. It also serves as an industrial feedstock for fertilizer and chemicals. And it's also used in power generation very heavily, and has also made its entrance into the transportation sector. Now, on top of its widespread use, it's also considered the cleanest among the fossil fuels, in that it produces less carbon dioxide when it's burned, and thus it plays an important role in the energy transition. So it is conceived to help reduce pollution, and basically it's considered the transition fuel more broadly. So overall, it plays a really critical role in today's energy system, and also plays an important role in a range of energy environmental policies. So that's why it's important to have a good sense of the price development, so that it can inform those government policies. So just think about greenhouse gas emission reductions, how to use public land, so to give permissions for mineral exploration and extraction, but also for the implementation of infrastructure policies. So price developments are important for deciding on permits for building LNG export terminals, for example. So overall, it's quite important for a number of policy purposes to obtain reliable forecasts of natural gas. And so this is going to be the topic of today's lecture. And the key question here really is, how different are natural gas prices from oil prices when it comes to forecasting? So can we simply use the models that I showed you last time that work well for forecasting oil prices and apply them to natural gas prices? Or are there some special features that we need to take into account when modeling natural gas prices, such as to obtain accurate forecasts. Now, here is a picture of daily spot oil prices and natural gas prices over the first 3 months of this year, and they already provide some insights into that question. So the red line is the WTI spot oil price, and I guess everybody can guess what that black line stands for. That's when the US and Israel attacks on Iran started. And since then, we have seen this rapid upward movement in oil prices, which this morning actually stood at 115. So I would have to extend the axis here all the way up there to capture the latest price movements. Now, what you observe at the same time is that the Henry Hub natural gas spot price, which is the reference price in the US, basically stayed flat over this period. Despite the fact that also natural gas has been a lot in the discussion in relation to the turmoil in the Middle East, and as a result of destruction of LNG facilities in Qatar mainly, which is a major exporter, with exports directed toward Europe. And in Europe, actually, natural gas prices have been much more volatile and affected by recent events. Now, you could ask, well, what's happening in the US? Why is natural gas basically flat? Why are prices not responding? And so the reason is that actually US exports of liquefied natural gas are limited by the liquefaction, sorry, facilities. And they were already running at 100% before the war started. And so that means that the supply of natural gas didn't really change. And so that's why natural gas prices didn't respond. So that's the first indication that when it comes to modeling the natural gas market and producing price forecasts, we might have to approach that differently. Now, at the same time, we observe this big spike at the end of January this year when oil prices stayed relatively flat. Now, for those of you who have been in the US at that time, you will remember that this was the Arctic blast. So we really had a very cold period. So kind of like a winter spell that was out of historical standards, and that was driving up natural gas prices locally or domestically, I should say. So, as I said, this gives reason to ask, well, what are the determinants of natural gas prices relative to oil prices, and how should we model that? And that's the question that we addressed in a recent paper that has just appeared in the Journal of Applied Econometrics this month, which is joined with Florian Huber, Thomas Lee, and Francesco Ravazzolo. And in that paper, we conduct a systematic evaluation of a broad range of forecasting approaches in order to predict the monthly average value of the real price of natural gas in the US for horizons of up to 2 years. So again, like last time for oil prices, the relevant frequency here is going to be monthly, even though I illustrated kind of some recent price developments with daily prices right now. What we want to focus on here is forecasting at the monthly frequency for up to 24 months into the futures. into the future. And once again, we're going to focus on the real price, given that this is the relevant object of interest, as I highlighted last time for oil prices. So it's really the relative price that matters. So how much we have to give up in terms of real consumption units to still buy the same quantity of natural gas when prices change. Now, there was some discussion last time why it should be the real price of energy that we consider generally. And I was actually very happy to see that I think on the same day or one day after the last lecture, even the Financial Times agreed with me, and they reported about the developments of the real price of oil in relation to the ongoing crisis. So when they were talking about the implications of the closure of the Strait of Hormuz, they specifically stated that or expressed things in terms of the real price of oil to show how bad things could get. And I think we're actually on the way there. And what the price developments of the real price would be to come close to previous peaks. And here in their notes, you see that they deflated the nominal price by US CPI, which is exactly what I outlined last time as the strategy of obtaining the real price. And we're going to pursue the same strategy today when we talk about the real price of natural gas. But I just wanted to kind of like add that on and link back to what we discussed last time. Now, having said that, of course, and I want to emphasize that again because it was also part of the discussion, you can, of course, always map real price forecasts back into nominal terms by adding back in a forecast for inflation. But again, for decision making, what matters, it's really the real price of energy. Okay, now on top of focusing on the monthly average forecast of the real price, another dimension that we want to consider here is to do so in real time. So we want to take a real-time approach to forecasting natural gas prices. And in order to do so, one of the contributions of the underlying paper here is to construct a real-time database that contains a large set of relevant predictor variables to reflect really what a real-time forecaster would know at the point in time when he or she generated the forecast. So we want to mimic as closely as possible the data constraints encountered by a real life forecaster. And that means to take lags in data releases into account and also capture subsequent revisions of data. So we compile a set of real-time vintages here in order to reflect both aspects here. Now, as I already pointed out, our focus here is going to be on the US natural gas prices. And the reason is basically that natural gas spot markets have been around since the late 1990s. So there was competitive spot pricing for a long time already because deregulation started in the early 1990s, where natural gas prices were really determined by the standard fundamental forces of supply and demand. Whereas in other countries, natural gas contracts were or are still linked to oil or some other non-market pricing mechanisms. So, for example, in Europe, you still had up to the mid-late 2000s natural gas prices indexed to oil. So they were not fluctuating independently of oil. And so that's why for now we focus on the US, even though, of course, there's also interest, I guess, on natural gas price developments in other regions, but that might call for a different set of models and could be a very interesting avenue for future research, actually. But yeah, for now it's just the US for us, and that's also already an indication that, in contrast to the oil market, which is really a global market, natural gas markets are still more fragmented. They are more regional, and price developments are not harmonized across these different regions. And once again, that influences how we think about forecasting models. So in fact, we're going to examine a number of different forecasting methods here. We're going to start off by looking at existing forecasts that I would describe as model-free, that are available because they are put out by certain organizations, or they are informed by the futures market. So in a way, they can be taken off the shelf. And so in order to establish a benchmark, I want to start by evaluating the out-of-sample forecasting performance of these model-free forecasts before moving on to designing our own set of models. And there we're gonna basically investigate the forecast accuracy that can be derived from four classes of models that differ both in their complexity and the economic or informational content. So we're going to start off very simple with the typical set of models that just exploits past price dynamics, so a range of autoregressive and ARMA models. Then we're going to turn to economic models of the domestic natural gas market, which kind of follow a little bit the blueprint of the economic models of the global oil market that I showed you last time, where we want to think carefully about the underlying fundamental drivers of natural gas prices. So what determines natural gas price fluctuations? Then there's another class of models that exploit basically the fact that energy prices at times co-move strongly. So here we're gonna exploit basically the co-movement between natural gas and oil prices due to the fact that oftentimes they are produced jointly. In fact, the reason for indexing natural gas prices originally to oil prices is that natural gas was just a byproduct of oil production. And so it was not considered as sort of a fuel on its own, if you will. And we're going to see to what extent this relationship between the two main fuel prices can be exploited for forecasting. And then the last class is what I call integrated markets models. So there we want to basically jointly model the natural gas market domestically, but also establish a link with oil prices. So that is the most comprehensive among the four model classes. Now, we also then, after having examined each and every model in their own, or model class in their own right, we also want to explore potential benefits from dynamic model selection and forecast pooling. So whether we can further improve on the forecast accuracy by basically combining the forecasts obtained with different models. Okay. Good. So let me start by describing the forecasting environment that we're going to operate in. So our target variable is the average monthly value of the real spot price of natural gas at the Henry Hub. So this is the benchmark price in the US. And for Henry Hub, we have available spot prices both at the daily and the monthly frequency from the US Energy Information Administration starting in 1997, which will also determine the starting point of our out-of-sample evaluation period. Now, before 1997, the Wall Street Journal actually released spot price data back to 1993. And before that time, basically, we had several price indicators for natural gas at the wellhead, which were kind of like the relevant prices at different trading hubs before Henry Hub kind of like emerged as the dominant spot price hub. And so we're going to use the average sales price here, which goes back until 1976, in order to construct a long time series of prices to be used in estimation of our models. Now, as I said, we find ourselves here in a real-time context, so we're trying to mimic it as closely as possible. So we're gonna construct real-time data vintages that only reflect the information that was available to the forecaster at the time the forecast was generated, which means that we're gonna keep track of data revisions over time, and we also take account of the lags in data releases, which then means that we need to design some nowcasting rules in order to obtain a balanced data set that we can use in estimation and forecasting. So we're going to devise some simple nowcasting rules in order to fill in the data gaps at the end of each vintage, inspired by the time series properties of the data. So we're going to do that on a predictor variable by predictor variable base and really see what is the best way to try and obtain a good proxy for the missing data at the end of each vintage. Then, as I mentioned before, we focus on the real price. Now, while the nominal spot price is available in real time, when deflating it with the US CPI, we need to take into account that consumer prices are released with a lag of 1 month, and that they are subsequently revised. So here we are updating the vintages from some earlier work of mine, and we now cast that missing observation at the end with the average growth rate of inflation over the preceding years, all the way back to 1976, basically. Then we're going to generate out-of-sample forecasts recursively, where the first estimation period goes from January 1976 to January 1997. And we then gonna update that by adding one more monthly vintages as we move through time. And the evaluation period spans all the way from February 1997 to February of 2024. Now, our evaluation criterion for the point forecast is the mean squared prediction error, and we specify the loss function in terms of the level of the real price of natural gas, which is typically what people care about. So the price in dollar terms, in real dollar terms. And so the common benchmark, just as for oil prices, is the no change forecast here. So the monthly random walk without drift. And the forecast horizons span from 1 month out to 24 months in 3 months intervals, basically here. Okay, so let's start by considering the model-free forecasts. So we're going to exploit first the fact that spot price data are available at higher than monthly frequencies. So basically, each trading day will give us a price quote that reflects the information on that day. And so there's a recent paper by Ellwanger and Snodden where they make the case that the end of month spot price yields more accurate forecasts for oil than the monthly average oil price. Now, actually, that question was first examined in some earlier work of mine in relation to forecasting the quarterly price of oil, where we also established that the most recent monthly price is much tougher to beat than the average over the quarter. Here, the idea is a similar one, namely that the end of month observation, so the observation of prices on the last trading day of the month is more informative, yields more accurate forecasts than the average over the month. So that's the first model-free forecast. So where we're going to compare forecasts generated with the last observation of the month, so on the last trading day, versus the average over the month. Then the second model-free forecast is obtained by turning to natural gas futures markets. So here we have the futures price available for contracts with different maturities, so that expire at different points in the future, and that is considered the aggregated information of market participants, and that might have forecasting power. So the way that we're going to model that here is by taking the spread between the Henry Hub futures price age periods from now, so for contracts that expire age periods into the future relative to the current Henry Hub spot price, then we're gonna deflate this future spot price differential with the expected value of US consumer prices or consumer price inflation, which we just extrapolate based on recent inflation developments. And then we're gonna map that into the real price by multiplying this with the real Henry Hub spot price today to obtain a forecast age periods into the future in real terms. And the third model-free forecast is derived from experts at the EIA. So in their short-term energy outlooks, they regularly publish forecasts of the nominal natural gas price. But for the Henry Hub spot price, they only start reporting forecasts from August 2005 onward, which means that we have a shorter evaluation period here in order to assess the out-of-sample forecasting performance. Plus, the forecast horizon is not consistently reported up to 24 months, so that varies depending on where you are in the year. So it basically fluctuates between 1 and 2 years out, but we have data consistently available for every month up to 1 year. So that cuts our the possibility of the forecast horizons that we can evaluate a little shorter than what we can obtain with the other forecasting approaches. Okay, so what do we find? Well, so here I show you the average mean square prediction error ratios relative to the monthly no change forecast, where, as you know, a number below 1 tells us that the model outperforms the benchmark. A number above 1 tells us that the benchmark wins and the model doesn't manage to beat the benchmark. So what do we find? Well, for the end of month no change forecast relative to the monthly average, we find that at Horizon 1, we have substantial gains in out-of-sample forecasting performance. So we have a very considerable reduction in mean square prediction error. But to some extent, that's not totally surprising, given that the last daily observation of the month obviously contains much more up-to-date information relative to the monthly average. But what you can see as well is that that informational advantage does not persist. In fact, it dies off relatively quickly. We still have some minor gains at the 3-month horizon, but after that, the monthly average price actually produces more reliable forecast than that one observation on the last trading day. Now, turning to the market-based forecasts, here we see that futures prices mapped into real prices through the futures spot price model that I showed you before outperforms the benchmark at all forecast horizons, sometimes significantly so. And the largest gains are in this medium-term segment here from 9 to 15 months out. Okay, so now when we turn to the EIA experts, as I said, that's not directly comparable because we have only a shorter evaluation period starting in late 2005. And what you see is that the EIA experts really don't do well at short horizons, but they do particularly well at 9 and 12 months out. So that's the best forecast. Now, to put those numbers into perspective relative to the other two model-free approaches, I repeated that exercise, or I'm reporting the average mean square prediction errors for the same evaluation period here. And what you see is that for that shorter evaluation period, the end of month no change forecast at the 1 month horizon is even more impressive than before, but the same pattern holds, namely that informational advantage goes away very quickly. Now, the futures market overall doesn't do as well anymore over that shorter evaluation period, but the overall pattern still goes through. So overall, what we can say is that at the very short forecasting horizons, the end of month no change forecast is the best, and then at intermediate and longer term horizons, the market-based forecast is helpful. And the EIA experts, I mean, I wish we could evaluate them for longer horizons. Would be really interesting to see whether the expert information really would come through there as well. But unfortunately, we don't have these forecasts available. Okay, now, what is the drawback generally of these model-free forecasts? Well, we don't really know what drives those forecasts, right? So we don't know how the experts make up their mind. We don't exactly know what information it is that traders use in the futures market. And so that begs the question, well, can we improve upon those model-free forecasts by designing a set of alternative models that are characterized by specific predictor variables that are derived from economic theory or market insights, so specific institutional features, and how do they compare to each other and to the model-free forecasts. Okay, and that's the task that we want to take on next. So we want to evaluate the forecasting performance of these 4 different classes of models that I mentioned to you before. And we're gonna start with the standard, which are just parsimonious time series models that exploit the dynamic relationship of the current price with its own past. And so here is the range of models that we consider. So we start with the simple ARMA 1-1 model. And there you can see we have a lot of numbers in bold that are smaller than 1, indicating that that model performs better than the monthly random walk benchmark. But at first glance, it doesn't seem to outperform, for example, the futures market. Now, if we basically move on to the second model, which basically takes into account the fact that it is not clear a priori whether the log of the real price of natural gas is a unit root process or not. So this model basically imposes a unit root on the ARMA 1-1 process, but as you can see, that doesn't really help with forecasting, suggesting that this process is not well described by a near unit root process. The same is true for the ARIMA model. Then we consider a bunch of autoregressive models estimated both with least squares methods and with Bayesian methods, where we rely on Domenico Giannone's prior selection determined by the marginal data density. So we outsource basically the prior selection to the marginal data density. So we update it as we move through time. And we consider different lag lengths. 12, we start out with 12 months, 12 lags, so a full year worth of lags to capture the dynamics, inspired by the fact that long lags is what seemed to work well in oil price forecasting. Then we have the Akaike information criterion determine the lag length dynamically. So we re-optimize at each point in time, and we impose an upper bound of 6 lags here for parsimony. And then we also just fix the lag length to 1 to see how much that matters. So what you see is that the autoregressive process, or the autoregressive model estimated by least squares with 12 lags, actually has a hard time beating the random walk. So it's mostly tight with the random walk. Now, if we allow for some Bayesian shrinkage, we can achieve some improvements at medium and long-term horizons. But for natural gas prices, it seems that longer lags are really not desirable, because if we then have the model, the lag length determined by the AIC criterion, we see improvements relative to the model with longer lags. And we also see that basically Bayesian shrinkage does not make much of a difference here relative to least squares methods. And that holds also up for when we impose just one lag. So the sweet spot seems to be somewhere in between 1 and 6, independent of the estimation method, again with mean square prediction error reductions becoming more pronounced at longer horizons, but with no clear pattern between the autoregressive models with the AIC and just one lag. Now, we also consider exponential smoothing, which is another way to just exploit past price dynamics, where you discount information further in the past more than more recent information. And what you see here is that does really badly at the short horizons, but it yields substantial gains in the long run, right? So here we're even outperforming the futures market right now with this very simple approach of exponential smoothing. So that's just past price dynamics, but and here is the takeaway that if you had to choose among that or within that model class, you would probably go with exponential smoothing for the medium to long run, and with the very parsimonious autoregressive process in for the first 6 forecast horizons. Now, the question is, well, what happens, and can we do better if we consider the fundamental determinants of natural gas prices? So when we draw on economic models of the domestic natural gas market, where the price is determined by the interaction of supply and demand side forces. So here we need to think about what those determinants are, and economic theory and the particular structure of the natural gas market suggest to look at your typical market fundamentals in terms of quantities. But as I showed you in that earlier graph, weather is a particularly important feature of natural gas markets. So, because of the tight connection or the use of natural gas for heating and cooling purposes. And obviously, the macroeconomic environment, just like in the oil market, plays a role here as well. So let's think about what variables and what measurements we have available for these three different categories of determinants. Well, among the natural gas market fundamentals, we're going to use natural gas production. And there we're going to focus on dry natural gas production, which is actually a purified version of gas that is eligible for pipeline transportation. So that's natural gas production that is cleansed of other kind of contaminating compounds, which would be contained in what is called marketed natural gas production. So that contains other natural gas liquids that are sold typically separately, which is why we think that the purified versions or the dry production is actually the relevant measure for natural gas prices. We also gonna use natural gas rig counts, which is the number of active rigs drilling for natural gas, and that is an indicator for future production because it gives us a sense of how intense the resource development is. So how much natural gas will be forthcoming down the line. So that's like a forward-looking measure of production. We also gonna use inventories, just like in the oil market. So it's possible to store natural gas underground. And here we're focusing on working natural gas, which is the flow component of storage that adjusts to changing market conditions. And given that we want to model price fluctuations as being determined by market forces, that is the relevant measure. Now, just like with oil, we can also approach this not from the production side, but from the consumption side. And we're also going to consider total natural gas consumption. So that's the demand coming from all end users, households, industrial sector, commercial sector, and other and utilities, I think. But we can also break out residential natural gas consumption separately because, as it turns out, household demand patterns are determined differently than demand from other sectors, because other sectors have the capability to do so-called fuel switching. So they have the infrastructure in place that allows them to basically switch between natural gas and oil, depending on which energy source is basically the marginal determinant of prices, whereas households are locked in. They make their decision once and for all how to go about heating and cooling in their houses. so we can see whether that information is valuable in and of itself. Now, when it comes to weather, so as I said and illustrated already, variations in temperature are a direct measure of the use of natural gas, as is determined by the demand for heating and cooling. And so that can be a very direct measure of consumption that kind of like adjusts very quickly to weather conditions. Now, severe weather not only influences the demand side, but it can also impact the supply side by either disrupting the production of natural gas or the transportation thereof. So if you have some winter storm happening, that can influence also the availability of supply. So when it comes to our meteorological measures, we rely on so-called heating and cooling degree days that approximate the demand for natural gas. There's also a specific demand temperature index for residential energy use that is based off of these heating and cooling degree days, constructed by the Oceanographic Institute. And then we also consider a measure of temperature anomalies that captures periods of extreme heat or cold snaps. So everything that is outside the norm would show up there, and we want to see whether things like the Arctic blast have a particular influence on prices and have, most importantly, predictive power for price developments into the future. Now, when it comes to macroeconomic conditions, given that the natural gas market is really domestically focused, we need measures of the domestic state of the business cycle because that's the relevant determinant for price developments. And so the state of the domestic economy will, of course, also then influence natural gas consumption. So how well the economy is doing influences how much natural gas is used in industrial and commercial sectors. And so we're going to use US industrial production here as one of our indicators, given that natural gas serves both as a fuel, but also as a feedstock for production processes, for example, for the production of fertilizer and chemical products. Another measure is US capacity utilization rates. That also tells us how well the domestic economy is doing. And the Chicago Fed National Activity Index, which is readily available, is a broad-based measure that allows us to gauge also overall economic activity in the US. And we're also going to investigate the usefulness of the CEFNI. Okay, now we want to conduct our forecast evaluation in real terms, right? In a real-time setting, sorry. So we construct a real-time database that is compiled from a large set of sources. So we're going to have data from the monthly energy review, from NOAA, from Alfred, Fraser, and the Chicago Fed for the CEFNI. We construct monthly vintages ranging from January 1991 to February 2024, and I regularly update them at the end of each month, and they are available on my website. So given that today is March 31st, you know what I'm going to do this afternoon. And so you can yeah, you can find them there and download and hopefully do some other interesting work with those real-time data vintages. Now, we also backcast each vintage to cover data back to 1973 January. So even though we only look at data, or our estimation period starts in 76, but again, this database is supposed to be used for other purposes as well, I hope. And so we extended back into the past as far as possible. Now, as I mentioned before, we need to design a set of nowcasting rules in order to fill the gaps at the end of the real-time vintages. And we specifically tailor them to each time series based on the specific data properties. In particular, for the weather variables, we're going to exploit some seasonal patterns here. So just to give you a quick run through, so for production, we're going to take the annual log difference for the preceding year. So production is to some extent also influenced by seasonal patterns, right? So when you have the peak heating and cooling seasons, for example, inventories are a bit more standard. So they were taking the month-on-month change 1 year prior. Then for consumption, we're going to use a random walk nowcast coming from the same month the year before, again, to account for the seasonal patterns here. Temperature is considered a slowly moving process. So we're going to take the average value of the same month averaged over the past 10 years. And well, capacity utilization and the CEFNI are standard macro measures. Here we're going to use exponential smoothing. And for industrial production, we're just going to extrapolate based on the average monthly growth rate over past observations. So here's just an overview of the data contained in our real-time database when each and every individual series starts, what their unit is, where the data are coming from, how much of a delay there is, so how many missing observations you have at the end of each vintage. And as you can see, that changes also over time. So statistical agencies have gotten better in releasing more timely data. Here's a summary of the nowcast rule that's applied to each series and whether they are subject to data revisions or not. Again, you can find more information in the paper as well as the database on my website. Okay, so we're going to use, again, reduced form vector autoregressive models for generating out-of-sample forecasts based on these economic indicators. In fact, our baseline model contains, obviously, our variable of interest, so the log of the real price of Henry Hub natural gas. Then in terms of the fundamental determinants, we have dry natural gas production, rig counts, and working inventories. We include those variables either in log levels or monthly growth rates to also see whether the transformation of the variables matters. We're gonna, in the baseline model, use capacity utilization as our indicator for the domestic economy because that seems to have been least affected by the COVID-19 pandemic. So capacity utilization does not show sharp outliers, even though actually it doesn't seem to impact the forecasting performance when we replace capacity utilization with industrial production. or the CEFNI. And then for the weather variable, we're going to use the demand temperature index as our benchmark weather variable. And once again, we also gonna investigate the role of the number of lags here. So ranging from a relatively highly parametrized model with a large number of lags to more parsimonious models, which might help with forecasting performance. Okay, so here are the first results for when the fundamental variables are included in monthly growth rates. Again, for models estimated just with least squares, with Bayesian shrinkage for varying lag length. And just like with the autoregressive models, we can see that long lag dynamics here really doesn't pay off in terms of forecasting performance. Bayesian shrinkage helps somewhat, but actually, the more we restrict the lag length, the better the mean square prediction error ratios get. So we basically have substantial reductions when we have models with just one lag and all these predictor variables. And once again, with such a short lag length, then it doesn't matter whether we estimate the model with least squares or with Bayesian methods. Now, when we turn to log levels, again, here we're even more penalized in terms of long lags, but we're having some gains when we move to the more parsimonious models. So the overall takeaway here from entertaining a comprehensive model of the domestic natural gas market is that the Bayesian VAR with one lag seems to be performing best overall. Maybe at this point, I should also mention that you won't see any stars from here on out, because given that we're in a real-time context, the typical tests do not apply. So we didn't do any kind of like tests for statistical significance of the out of sample forecast performance improvements. So here, all you can do is to rely on the number itself. Okay, now once again, like with the oil market, the question is, well, is there some scope for improving forecasts by allowing for time varying volatility? Just like with the oil market, also the natural gas market has undergone substantial transformations. There have been changes in regulation, mostly deregulation. The market structure has changed, and of course, all of that can impact the forecasting performance. Now, as we saw, given that the natural gas market is influenced heavily by weather conditions, so these shifts can happen very quickly sometimes, and can result in an increase in price volatility. Now, without showing you detailed results, what we find is that in a forecasting context, allowing for time varying volatility does not yield systematic improvements in terms of forecast accuracy, but we find some gains at longer horizons. And that's consistent with what we saw last week or last time with the oil price forecast. The stochastic volatility there really helped a lot at the 1 to 2 year horizon. And we find similar results for natural gas. So it matters some, but not in a systematic way to be able to claim that time variation is the key feature here. Whereas, as we saw, it was relevant for especially in the oil market, both for price and consumption forecasts. Now, let's move on to the third class of models, which are these energy price models that are based on the idea that natural gas is linked to crude oil because of the possibility of fuel switching. So, especially power plants in the generation of electricity have the possibility to swiftly move between natural gas and crude oil as the primary source of energy, which suggests that we want to model that relationship using bivariate models. However, there is no mechanical link between those two energy prices, given that the two fossil fuels are not perfect substitutes, right? So they all have still different characteristics. So the quality is different, and the energy content, for example. That's why we cannot kind of like take it as a given that modeling these or using these bivariate models will result in better forecasts. Also, as I mentioned before, there is no oil price indexation for natural gas in the US. So that feature might be more worthwhile exploiting in or for European natural gas prices, because a fair share of the market is still based on long-term contracts where the price is indexed to oil. Now, what is very interesting is if we look at the co-movement between natural gas prices and crude oil prices over time, that relationship has gone through different periods. So there seems to be evidence for a co-integrating relationship from 1993 to 2010, which then, however, has broken down as a result of the shale gas revolution that started in 2006 and really took hold in 2010, where both prices started to diverge. And that decoupling was underway until 2016, when we had the first LNG facilities that allowed to transport or to export basically natural gas, which initiated a recoupling phase. And so this is basically what you see here, where I plot the relationship between the nominal Henry Hub price and the WTI crude price. So you see a strong co-movement in that first period. You clearly see the divergence where both prices really move into opposite directions over this shale gas period, where there was basically too much gas around because it was not possible. It was landlocked basically, so could not get it to other markets, which started to be a possibility with the opening of the first LNG export facility. And now you can see that apparently there is kind of like some co-movement going on again, so the two markets start recoupling. So we're going to design a set of price spread models that are based on the maintained hypothesis that the nominal spot prices of natural gas and crude oil are co-integrated, and that suggests that current deviations of spot prices have predictive content for cumulative changes in natural gas prices down the road. So that means we're using the price spread between Henry Hub and WTI as a predictor for the cumulative changes in Henry Hub. So we're going to estimate here alpha and beta in our price spread model, and then we're going to map that into forecasts of the real Henry Hub price along the same lines as we did for the futures market, where we used the future spot price differential. Now, unfortunately, these models do not do well, maybe not unexpected. So independent of whether we estimate both alpha and beta, or we set the constant to 0, there are only marginal gains at the 1-month horizon, but nothing after that. Now, in the paper, we also allow for Markov switching dynamics in alpha and beta to account for the fact that the underlying market structure or that co-movement has changed over time, but also that only yields some sporadic gains. Now, here we look at the average mean square prediction error ratios, right, over that long evaluation period from 97 to 2024. Now we can get some insights why the price spread models perform so poorly if we track the evolution of the MSPE ratios over time. And in fact, you see that these models actually did very well until the co-integration relationship broke down. Now, we don't obviously, as a real-time forecaster, we don't know that this co-integrating relationship went away as a result of the shale gas revolution. So we don't have the possibility to model that explicitly. But of course, with hindsight, we can track when the deterioration in forecasting performance happens, and that aligns well with that breaking point as established according to some statistical tests in a recent paper by Stock and Zaragoza-Watkins. Okay, so you can clearly see the co-integration relationship breaks down, and the MSPE ratios shoot up across all forecasting horizons. Now, alternatively, we could also have modeled that relationship between the two energy prices in the form of bivariate VAR models. And here we consider two specifications. One where both prices are in log levels, which allows for implicit co-integration relationships. And in the other specification, we impose co-integrating restrictions by using a vector error correction representation. So let me be quick on that because there's nothing really interesting here. So the role of co-integration here in the bivariate VAR models, where we impose co-integration, does not help us in out-of-sample forecasting performance. The unrestricted VAR models do a little bit better. Again, the lag length plays an important role. And as it turns out, in these bivariate models, a longer lag length is actually preferred over a more parsimonious specification. So if anything, the takeaway from these energy price models is that the BVAR12 model that implicitly allows for this long-run relationship is the only model that shows any promise at all, but doesn't yield substantial improvements here. Now, the last class of models is a hybrid model where we integrate basically own market fundamentals with cross-market fundamentals. So we essentially augment the economic model of the domestic natural gas market with the real WTI oil price, drawing on the insights from model classes 2 and 3. And here we also consider models with and without stochastic volatility. And the key takeaway is that these combined models do well, and the best performing one is one that includes stochastic volatility. So it seems in this larger model, allowing or explicitly modeling time-varying volatility helps. Okay, so where does that leave us? After this systematic evaluation of a large set of models, well, based on pairwise comparisons, so the model versus our benchmark, it seems that the BVAR1 in the class of economic models of the domestic market is overall the best performing model. However, what we can do is we can go a step further and jointly assess the value of the entire model space using the model confidence set proposed by Hansen et al., which actually ranks the models by comparing them not just pairwise, but by comparing them jointly. Now, if we apply that criterion, then we find still that the BVAR1 among the economic models ranks highest together with the futures-based forecast. Now, unsurprisingly, at the very short horizon, namely 1 month out, the end-of-month random walk dominates, and at longer horizons, we have exponential smoothing and some of the economic models with time-varying volatility. Okay. Now, what we can do is to exploit this ranking of the based on the model confidence set in order to kind of like pool our forecasts. So, given that there is no clear winner among the individual models, we can basically just combine forecasts and see whether that helps with accuracy. Because as we saw, different models matter at different horizons. And so maybe by combining their informational content, we can achieve further improvements. On top of that, as is well known, forecast combinations also help to guard against forecast failures. So we proceed in 2 steps here. So first, I want to show you as additional motivation how the forecast performance of individual models changes over time. So to get a sense of how stable or unstable they are. And then we're going to propose a new dynamic model selection criterion for combining forecasts based on the MCS. And then we're going to pool our forecasts either by applying equal weighting or inverse MSPE weights. Okay, so here is some evidence about the forecasting performance over time. So here I show you how the MSPE ratios evolve over time. And as you can see, both at short forecasting horizons, like 3 months out, and long forecasting horizons, here 24 months out, there is quite some heterogeneity in how models perform, which models do well. Some improve over time, some deteriorate over time. Again, that is suggestive that forecast combinations might really help us here to improve the performance. And so here I show you MSPE ratios for various forecast combinations. In a first instance, we're just going to use all 60 models. That's the total that we have in our model set, and we apply just equal weights to the forecasts. What we see is, yes, we improve upon the benchmark, but again, the improvements do not seem to outperform individual models just yet, no matter whether we apply equal weights or inverse MSPE weights. Now, then we want to move on to parsing our model set somewhat. So we're only gonna combine forecasts of models that end up in the 75% set of the MCS. And the important thing to note here is that the MCS is applied dynamically. So we're gonna basically select, or the model set can change at every point in time. Okay, so we will never have necessarily the same forecasts in the pooled forecasts. And what we see here is that at longer horizons, by just combining models that end up in the 75% set, help quite a bit with reductions at the 1 to 2 year horizon. Okay, so here we're getting some numbers that start to look interesting. Now,
Christiane, sorry to
Yes.
interrupt. We still have 10 minutes.
Okay,
So
that's
I don't know
perfect.
if you
Yes.
want to manage. Okay.
I should finish before that, and then we have some time still for
Very
discussion.
good.
Thanks
Very
so
good.
much,
Thanks.
Laurent. Um, so now, given that we already saw this change by throwing out some of the models, right? The question is, what if we become more restrictive, right? So, and we do that dynamic model selection by applying a stricter criterion. So here we're going to limit the forecast combinations to models that are ranked first or second according to the p-values implied by the model confidence set. So the model confidence set will always assign probability of 1 to the highest ranked model. So that is always going to be included. And then it has p-values for the kind of like or the ranking criterion then comes with p-values for the next set of models. And so all the models that have the second highest p-values will be included in the forecast combination. All the other ones will be discarded. And here we're going to determine that ranking recursively, meaning that selection or ranking is based on the entire past forecast performance of the models. So that's the model selection. Once we have the selected set of model, we're going to again apply equal weights or inverse MSPE weights, and we see that we get some more mileage out of that relative to the confidence set with 75% confidence level, but not too much. Okay. Now, that means, or kind of like the reason here is that the p-values are still informed by the entire history of forecasting performance. So essentially, bad forecasts in a way are never forgiven, right? So, which is why we want to now do the selection on a rolling basis. So where we only consider the forecasting performance of the models over the past year and apply the selection criterion with the first and second highest ranked to just that limited amount of forecasting performance. And here we're really gaining some mileage. So we're getting actually a set of impressive MSPE reduction. So our MSPE ratios, kind of like these are dream values, right? So for any forecaster who has ever done out of sample forecasting, so getting MSPE reductions of like 50% relative to the benchmark is quite something. So this very strict criterion seems to help a lot in terms of improving the out of sample forecasting performance. And again, it doesn't matter how the surviving or the forecasts of the surviving models are aggregated, equal weights or inverse MSPE ratios or MSPE weights yield more or less the same numerically. So here is an overview of that model selection just to illustrate that it's really not the same set of models and that that dynamic selection matters a lot because based on what I showed you before, the forecasting performance really changes quite a bit over time, right? So this was this picture here that, of course, directly translates to the models that are selected. And so what we find here is that, for example, in the first part of the out-of-sample evaluation, so from about 1997 to kind of like the early 2000s, the price spread models do kind of like show up in the model selection a lot. So that means when the co-integrating relationship between oil prices and natural gas prices was in place, right? That has a lot of predictive content. Those models were doing well, also in line with the recursive MSPE ratio plots that I showed you before. Now, another feature that you can see of this dot map, so where again, the colors relate to different model classes, and actually this little black dot always shows that this is the best performing model, so the highest ranked among the selected ones. Again, here you see the price spread models being most of the time the best performing models, and they totally disappear in later periods because their forecasting ability just goes away after the breakdown of the co-integration. Now, what you see as well is that the economic models here in red, so of the domestic natural gas market, they show up consistently over the entire time period. So fundamentals always matter. That's the key takeaway here. Now, when it comes to the first row, so in yellow, you have the futures market, and you see that futures prices really didn't add a lot in the early period. They were almost never selected, but they become much more relevant in the more recent periods where they are oftentimes the most or the best performing model at the 1 year horizon, consistent with the results that I showed you for the model-free forecasts, right? Now, the question is how should we go about that in practical terms, right? So here to produce this dot map, we really updated the data sets in real time every period. We estimated all 60 models and evaluated them. We kept track of their performance in order to do that. That might be tedious to do if you're a real life forecaster and you don't want to engage into this big model update when at the end of the day you only select a handful of models whose forecasts you want to combine. So what we suggest you can do is basically to just see, okay, which models are selected most recently, say over the past year or two. And this table gives you a sense of that. So for short horizons, the end of month random walk, one of the economic models, the BVAR 12 with the predictor variables and logs is selected. The bivariate model, which is interesting. So apparently the recoupling of oil and natural gas prices seems to have happened in part, again, some predictive power here. And then the big integrated markets model here also helps at the 1 month horizon. Now, what consistently helps over all forecast horizons are once again the economic models. The models with stochastic volatility and the futures price are the dominant ones at longer horizons. And so you could basically use this table as a guide for the forecasts or for the models that you want to use to generate forecasts with. and then either combine them, or if you're interested in a particular horizon only, let's say you're a long run forecaster, then you might want to either select one of those models that's easiest for you to update, or use combinations there as well. So we're at the time to see what the main takeaways are of this analysis. Well, it turns out that the most useful model across all horizons is an economic model of the natural gas market that contains the fundamental determinants of natural gas prices, where the baseline predictor variables are included in log levels, with a fixed lag length of 12, or selected by the AIC in real time. So if I had to give a recommendation for the one model that kind of like strikes a good balance across all forecast horizons, it would be the VAR 12 in log levels. But as I've shown you, forecast pooling is really beneficial, especially in the long run. So for horizons beyond 1 year, I would recommend combining forecasts from the default model together with futures prices and the integrated markets model, as well as the bivariate energy price model, by using equal weights to aggregate the forecasts. And at horizon 1, it is useful to substitute the futures with the end of the month random walk, which really has a lot of informational content at the short horizon. So the overall conclusion of today's lecture is that, well, not all energy prices are alike when it comes to forecasting and designing forecasting models. It's really key to take the institutional structure into account when you design forecasting models. Also, the selection of predictor variables should be informed by market characteristics. Is it a global market, a domestic market? What variables really matter for determining prices? Again, what stands out with natural gas prices is really that weather conditions play an important role. Now, as we saw as well, selecting the best performing models in real time by applying a dynamic criterion, here the model confidence set, and then combining forecasts can really further enhance the forecasting performance and yield impressive gains in terms of mean square prediction error reductions. I think this is a very promising research agenda. So there has not been, as I mentioned in the beginning, a lot of systematic analysis for natural gas prices. But given the growing importance of natural gas as an alternative fuel to foster the energy transition, I think more attention ought to be paid to that market and to generating useful forecasts that can inform policy decisions. And so here I list a number of avenues for future research that I consider very promising. So what one could explore further is whether there are other approaches out there for dynamic model selection, and see whether that can outperform our novel MCS criterion. So here I'm thinking of Bayesian model averaging, Bayesian predictive synthesis, all sorts of selection and combination approaches that are out there in the literature, could be useful to investigate also for natural gas price forecasts. Now, like with oil prices, we have focused on the monthly frequency for generating forecasts, but of course, that's the relevant forecast horizon for firms, households, policymakers, but maybe not so much for financial market participants who have an interest in higher frequency forecasts. So it would be really interesting to design forecasting models at the daily and weekly frequencies. Now, the why do I say design forecasting models where we cannot take that set of models and easily just estimate them at daily and weekly frequencies because the predictor variables are just not available at these higher frequencies. And so that really calls for a different set of models. And then another avenue is so far we have only focused on the accuracy of point forecasts, but of course, density and tail forecasting could also be very interesting. And that actually brings me to foreshadow what we're going to cover in the next lecture, which is tail forecasting in oil markets. So we're going to revert back to oil prices, which I think, especially these days, is particularly important to ask the question, well, how bad can things go? And do some informed risk assessment down the road, which particularly in at this current juncture with the turmoil in the Middle East, hopefully should be useful for practitioners. And my plan is actually to do some real time tail forecasting and risk assessment as the end of this month. So stay tuned until next time, and I hope you're going to join again. And that's it for today. Thanks so much.
Thanks a lot, Christian. Thanks a lot, really, for this exhaustive presentation, very clear, and on a topic that we are not used, at least less than oil prices, but gas prices are obviously super important now. We have maybe a time for one or two questions from the audience, if there are. Do not hesitate to raise your hand if you have one point that you would like to highlight or anything. Okay, so that is saying thank you. Maybe one quick question, Christian, that I have. At some point, you were using weather conditions, okay, in your forecast. I was wondering why you don't use a weather forecast when you want to forecast over a long horizon. Do you have access to the kind of forecast? Did you try, or do you have any insight on this?
Well, given that the weather conditions are part of our vector autoregressive system, right? I mean, we could potentially kind of conditional forecast, but I mean, I mean, I'm not saying that the VAR models that we have are great at forecasting weather. They are for sure not, right? But I think if you were to impose sort of future weather conditions, that would kind
Yeah,
of be more along the lines already of a scenario, right? So I
scenario.
mean,
Yeah, yeah.
and weather forecasts are also kind of like typically not that great. So I mean, it would be the question whether that would help with forecasting performance. But yeah, no, we just condition also because you have like really the extremes. Yeah, sometimes in kind of like in very short time horizons, right? So the Arctic blast, I mean, there were the weather systems, right? You could track them. They were evolving, and you could see when they would hit basically certain area. So there was some, but I think that might become more relevant to exploit these weather conditions as they evolve in real time when you move to a higher frequency. So especially because it's in kind of like at the monthly frequency, we were exploiting like the anomalies or stuff that's sort of out of the ordinary, looking back, right? So I think yeah, that's
Okay. Yeah,
my
it's more
opinion.
conditional forecast. Agree.
I would think so, yes.
Josephine?
Good morning. More on the philosophical side of questions. I think what I found very interesting is when you were describing the differences in market structure. So with oil having this very global market being super homogeneous across regions, and that's we're not there or may never get on that side on the natural gas market. I think I want to know what your impression is because you had this. So the decoupling of the prices seem to be driven also by regional developments whenever fracking sets off in one region.
Mhm.
But that reverted a bit towards the end of the sample. Do you see kind of a perspective for this market to become more global, or would you say too much investment would be needed to make that really happen? I mean, I want to get a sense of how substitutable the goods will
Mhm.
become. Yeah, that's kind
Well,
of open-ended question.
yeah, no, thanks for the question. And kind of like for, given that we're trying to project prices into the future, let's also project models into the future, right? So how useful are those models potentially gonna be in light of market developments? I mean, this is the whole point of the design of the model, right? That you keep abreast of market developments and try to incorporate them into the model. So. I guess the question is a little bit kind of like how long do we plan on rely on this on natural gas as the transition fuel, right? So I mean, is it really helping us to smooth or to bridge things from weaning us off of fossil fuels in general? And so it's like smoothing from oil prices to renewables and maybe nuclear or other sources of energy, right? And kind of like what do we project this how long that transition is going to take, right? I think people so far were very optimistic. Now, maybe the one good thing of the recent turmoil will be that it propels us to get back on the fast track, which we have over the last year at least backtracked, right? So back to fossil fuels. So it's kind of like it's this continuous back and forth, and it matters, as you pointed out already, in different ways in different parts of the world, right? So. However, having said that, my own personal perspective is that the transition will take longer than people want to acknowledge, or that people want it to last. So, in that sense, I see scope for more infrastructure development that would allow us to, or that would allow the natural gas market to become more integrated globally. I think we already made the first step. And it has become more integrated, or is becoming with the LNG shipments, right? That's what we saw in the aftermath of the Russian invasion of Ukraine. It has stalled a little bit right now, but I would hope that that picks up again. And so that should mean, I mean, going back to forecasting, that these models become more valuable down the road again. In fact, I had hoped to already see something a little bit when tracking the forecasting performance of these models, but I think it's still too early because I mean it takes a while to come back from such a bad performance, basically, right? So for the data to really pick that up, and maybe some other modeling frameworks that would allow to more active, I mean, that would allow the data to recognize, okay, that these regime changes would be helpful. I mean, again, we tried in a very, if you will, rudimentary way with Markov switching models, but you could think of modeling these co-integration relationships in a more smoothly evolving, time-varying fashion or something, and maybe so by discarding the past further, and it would pick up a bit more. But so that was the long answer to your question. The short answer is yes, I definitely see some scope there for also more or movement toward a more globally integrated market, and thus for those set of models. Okay, there's a
The
question
comment,
in
there
the
is a comment.
chat. Yes, a
Okay.
platform. Um,
Oh, question, sorry.
Yeah, question for the European markets. Uh, the answer is unfortunately not. I have not worked with the European natural gas markets, so I'm not familiar with the data sources there yet. I hope to do that. In fact, you could add that to the promising avenues for future research, right? But I wouldn't see I mean, that you can take the models that work for the US market and just plant them or re-estimate them with European
Mm.
data. Because again, um, my goal today was really to illustrate that the natural gas market, among all the energy markets, really requires some tailoring toward the institutional features, and they are very different across the regional natural gas markets. That's what I know. Um, but how to then model these differences or how to go about modeling these various regional markets, I haven't given enough thought to that yet. So sorry, I cannot really give a useful recommendation there yet.
Okay. Thanks a lot, Christiane. I think we can close the session now. Thanks a lot for your lecture. It's super useful, and hope to see you all at the next lecture in 2 weeks, I
Yes.
think.
Mhm.
Okay.
Okay.
Thanks a lot.
See
Bye
you
bye.
then. Bye bye.
Thanks a lot.